This is our final session of the first day, and it is our pleasure to have Bhaswar Bhattacharya speaking on higher order theory of graphons. Go ahead.
Thank you, Shobik. Thank you for the invitation. It's a pleasure to be here. So title's a bit over the top, but I'm going to talk about fluctuation theory of subgraph counts in random graphs sampled from graphons and their statistical implications. So this is a joint work with Anirban Chatterjee, who is a graduate student at Penn, Shoham Dan, who was a graduate student in Penn, who just graduated now at IBM, and Svante Jansson. So the talk will have three parts to it. The first part of the talk will be probabilistic, where I will talk about the asymptotic distribution of subgraph counts in random graphon models. The second part will be statistical, where we will try to use some of this asymptotic distribution to estimate and construct confidence intervals for subgraph densities of the original population graphon. And the third and the last part will be more combinatorial, where I will discuss some degeneracy issues of this limiting distribution and the structure of such degenerate graphons. And here we will see some interesting connections to things like quasi-randomness and other things. So this is a conference on graph limits. I'm sure everybody here knows what a graphon is and why it's important. But nevertheless, let me say a few words about background and motivation and start from the basic. So the basic model of a random graph, which we all know, is the Edwards-Renyi model, where every edge is present independently with probability P. We call that GNP. So this model has been studied widely by mathematicians, but for modeling real networks, this is a bit simplistic. So one way to generalize this is to have the inhomogeneous random graph model, where instead of having the edge probability P for all ij, you have a probability Pij for every edge. So the edges are still independent, and the probability of edge between I and j happens with Pij. So we denote this by GNP, where P is this matrix of probabilities. So several well-known network models are in this framework. So if you take P to be a block model, you get the SBM. In statistics, people study this thing called the beta model, where Pij has this logistic form, e to the beta I plus beta j1 over e to the beta I plus beta j, and several others. So the random graphon model is a variant of this model, where you replace this matrix by a symmetric measurable function. So a graphon is a symmetric measurable function, and you can use this to construct a graph in the following way. So the W random graph on n vertices is obtained as follows. You generate uniform random variables u1 to un, and you put an edge between I and j independently with probability wi uj conditional on the ui's. And we denote this by GNW, right? So graphons are continuum analogs of symmetric matrices, and if you take it to be, various choices of the W give you various well-known models. If you take the constant function, you get the Edwards-Renyi graph. If you take a block function, you get the block model, and so on. So a few words of background. So we know that W random graphs are dense. So you can easily compute what is the total number of edges in this graph. And an easy computation will tell you that the number of edges divided by n square will converge to the integral of W over the unit square. And we're always going to assume this is positive. So this graph will always have order n squared edges. So this is a dense graph. Now, there are many ways to make these parse. And the easiest way to do it is to add this sparsity parameter rho n in front of this probability. So the probability Pij is rho n times wi uj, where you let rho n go to 0. So we will not talk about the sparse regime, even though some of the results can extend to the sparse regime. I will primarily focus on the dense regime, but I just wanted to make the comment that something can be done if you allow sparsity. Okay, so the basic statistical question that you have, given a graph from this W random model, is how do you estimate this unknown function W? So this is the problem of graphon estimation, which has been studied extensively over the last few years. So here are some papers which started this field, and this has led to a long line of work. So we are not interested exactly in the problem of graphon estimation. We are interested in estimating subgraph density. So functionals of graphons, like the density of edges, the density of triangles, or homomorphism densities in general. So estimating densities of subgraphs given a sample Gn from this Graphon W. So this problem was studied first in this very well-known paper of Bickelchen and Levina, and they developed a way to estimate these quantities. So I write down here explicitly some of the subgraph densities which will appear in this talk. So the edge density, we already saw that. The triangle density is this thing here, WXY, WYZ, WXZ integrated over the three variables. The density of two stars, so two star is K1, 2. This graph with one central node and two leaf nodes, so the density of that. And for general H, you can write down the homomorphism density as the product of W over the edges of H integrated over X. So our goal is, given a graph Gn from this model, how do you estimate these functionals or functions of these functionals?
Just a quick question.
Yes.
Usually, just to clarify, motif, sometimes people mean induced subgraphs by that.
Right.
I'm
not doing induced.
Okay.
Yes, we could have done it, but we are not. Yes, yeah, that's good. This is non-induced. This is just copies. Yeah. So as I mentioned, and I might talk about a bit more in the end if I have time, that various interesting network functionals can be represented as functions of subgraph densities. So one thing that people look at is the clustering coefficient, which is essentially just the probability that three people are mutually friends, given that one is friends with both of them. And you can write this as the ratio of the density of triangles to two stars. So how do you estimate this quantity, or other related quantities? Okay, so let's try to see that how we can do this estimation and what can we say about the fluctuations of the natural estimate. So the subgraph counts, the homomorphism densities are nice functions in the Graphon space. These are continuous functions. And so a very natural estimate of the homomorphism density is the empirical density of H in the observed graph, the density of H in the graph Gn. So let's set up some notation for that. So for a graph H, we denote by xh of Gn the number of copies of H in the observed graph Gn. I scale it properly to make it into a density. So th of Gn is going to be my density, which is going to be essentially the copy divided by n to the vh. Well, it's not exactly n to the vh, but it's n to the vh up to some smaller order. And I have a multiplicative constant factor, which is just the size of the automorphisms, to take care of the various relabilities. So this quantity here is an estimate of the empirical density of H in Gn. And a simple variance calculation can show you that as the size of the graph gets large, this will converge to the true density.
So your normalization is such that it unbiased.
Yes.
Exactly. As if you would take the T of H at Gn, or you define your T of H. If you took the natural T of H at Gn, which would be the T of H at the empirical Graphon, that would be slightly biased.
Slightly biased, yeah.
It might be better.
Oh, yes. So in the statistical language, you will say that th of Gn is a consistent estimate for th of W because it goes to the true parameter as sample size increases. So the natural next question is, what is the distribution of this estimator? So this is a question in itself from a mathematical point of view, but this is also an important question because if we want to find a confidence interval for this parameter, we need something about the asymptotic distribution. So what can we say about that? So this quantity has been studied before by various authors, various people. Several of them are here in the audience. So Bickelchen Levina derived the central limit theorem for THGN or XHGN when H is cycles or H are trees, so some special types of H. For general subgraphs, the CLT was derived by Ferem, Elliott, and Ekabali. There is a recent related paper by Kaur and Rollin where they don't look at exactly this quantity, but they look at centered subgraph counts, where they first centered the adjacency matrix by the mean, and then look at the counts of the triangles, and they prove some CLTs. Now, all these results prove a central limit theorem for this quantity. So what does that mean? They show that this quantity is approximately Gaussian. Okay, so it turns out that in some cases, in fact, in many cases, the variance of the Gaussian can be 0. So the limit is degenerate. So this issue was first noticed and studied in this paper by Hadley, Pelekis, and Silakis, where they showed that the CLT can be degenerate, and they had some non-Gaussian limit where H is a clique. So this paper is the starting point of this work to study this degeneracy and see its implications. So let's try to explain in a very, very simple case why this degeneracy happens when H is just the edge. So when H is just the edge, everything is explicit. We can do a computation and we will see why you have this. So when the central limit theorem has variance 0 and what happens if it has variance 0. So let's start by defining the degree function of a graphon as just the integral of W over one of its coordinates. So if you look at the number of edges, this is just the sum over Aij, where Aij is the indicator whether or not the edge Ij is present or not. So let's do a little variance computation, right? So if I have to compute the variance of this is going to be the sum of the variance of the Aij plus the covariances. So what's the variance of Aij? Well, the variance of Aij is nothing but, you compute Aij squared minus Aij whole squared, and you get essentially the density of edges minus the density of edges squared. It's just a computation of the variance of Aij. And similarly, you can compute the covariance between Aij and Aik. So two edges which share a common vertex are dependent because of the uniform latent positions they have, right? The edges are not dependent, but because they share the same latent position, they are dependent. So you compute what it is. It's Aij, Aij, Aik minus the product of the expectation. And this turns out to be the density of two stars minus the density of edges squared. So very easy.
Sorry, can I interrupt you?
Yes.
I may have missed it. What's the exact model you're looking at? Are the vertex labels chosen uniformly,
yes,
or on a fixed grid?
They are chosen uniformly.
Okay, so that's
yes,
the standard
yes,
model. Okay,
yes, standard model. Yes. So that's why we have this covariance term. Otherwise, this doesn't exist.
Yeah.
Okay, so if you put things together, we have a quadratic term coming from the variance, and we have a cubic term coming from the covariance, but these are the constants here. So if you look at this expression and you note that, well, the variance therefore can be either n cubed or n squared, depending on whether this term here is 0 or not. So what is this term here? This term is the density of two stars minus the density of edge squared. So when is this term 0? Can this term ever be 0? So let's write this out. So this is the density of two stars minus the density of edge squared. So this is the square of the degree function. The 2 star is the square of the degree function minus the degree function squared. So this is nothing but the variance of the degree function at the uniform point. So this can't be 0, right? Whenever the degree function is a constant. So whenever the degree function of a graphon is a constant, this term is 0. So the variance becomes n squared from n cubed. So we say that a graphon is degree regular if its degree function is constant, and this is if and only if, this is when the variance changes from n cubed to n squared. And this condition is not something very, like strict, because lots of graphons are actually degree regular. The Edo-Shreni graph is degree regular. Stochastic block models with equal block sizes is degree regular. So what happens if you are in the degree regular case, and what happens if you are in the irregular case? Yes.
Only degree regular if you have the same on and off. If you have journal off.
Yes. So it's A, B, B, A. Right. Yeah. Exactly. Yeah. Yeah. The planted bisection model, I should say. Right. More correctly. Right. So Hadley et al. Showed that if the graphon is not degree regular, then if you look at the number of edges, if you center by the mean, divide by n to the 3/2. So remember, the variance here is n cubed. So standard deviation is n to the 3/2. Then there is a CLT. This is the classical regime. But this CLT can be degenerate. And in this case, the variance becomes n squared. So standard deviation is n. And in this case, the limit has a more complicated structure. So it has two components to it, a Gaussian component and an independent non-Gaussian component. So the Gaussian component has variance this, which is not very important, but the non-Gaussian component here is a weighted sum of centered chi-square. So it's a square of a Gaussian minus 1. So these are chi-square random variables which are centered, and the weights here are the eigenvalues of the Graphon W. So the Graphon, you can think of it as an operator. The weights are the eigenvalues of W. Not exactly, you have to remove the largest eigenvalue. Okay, so that's the limit. It has a normal part and it has a non-normal part, which is an infinite sum of centered chi-squares, weighted centered chi-squares.
Is that sum finite?
That sum could be finite for block models, but there are Graphons with countable spectrum, so it can go, but it's always countable.
But then, if it's countable, is this kind of variable well defined?
Yes, because the variance is with the second moment of lambda, and which is always the square integral of W.
Okay.
Yes.
Good.
Yeah. Okay, so this is what Hadley et al. Showed for the case of edges. In fact, they showed the result like this for all cliques of size R. So they showed that if something happens, there's a normal limit. If that doesn't happen, there is a non-normal limit which has a similar form. So in recent result with Onilban and Svante Jensen, we extended this.
So how does the spectrum appear? Because the spectrum would usually relate to cycle counts.
Yes. So yeah, so essentially, so I have a slide in the end to explain where this is coming from, but the moment, if you look at the moments of this quantity, you can check that the only terms that count, only terms that matter are the cycle counts. And so that's why you have the spectrum. Yes. Because everything else will be smaller order.
So is it method of moments type argument or what?
Okay, so this is good point. So Hadley et al. Proved this result using Stein's method and this result using method of moments. Okay. We don't use a method of moments. Yeah. Okay, so we extended this for general H, and so two things need to change if we have to extend this to general H. First, the notion of degree regularity has to be replaced by some notion of H regularity. So what is degree regularity? It is the density of edges passing through a point X. Well, this X is a continuum point, but essentially the density of edges passing through a point X is a constant. So for general H, the philosophy is similar. We look at the density of H passing through a point, but now if the graph H is not a symmetric graph, it depends which point of H maps to X. Okay? So we can write down this more formally as a graph on W is said to be H regular if you first map the eighth vertex of H to X and you look at the density of H where the eighth vertex is mapped to X, and then do average over the choice of P. Yes.
So it's not clear to me that that would be enough. I could imagine that, okay, now you get some condition, but maybe sometimes you need to calculate T tilde of X and Y where I fix actually two labels.
Yes. So this will be enough to understand the first order of degeneracy. So we have two layers of degeneracy. First, when the central limit theorem has this variance. This variance comes when two copies of H intersect at one point.
Right, but they could intersect in.
But that is next order.
But if that order you can just, you could now make the next order.
Yes. So we'll just get there in a second. So we also need the 2-point conditional homomorphism. We need that. But the definition of regularity doesn't need the 2-point, it needs the 1 point, but we will need the 2-point very soon. So next slide, I have the 2-point function. Here. Yeah. So in other words, the density of H, so what this means informally is that the density of H where some vertex of H is mapped to X is constant almost everywhere. And we have to be a bit careful because the graph H is asymmetric, so you have to be careful which A maps to which X. So if the graph is actually symmetric, it doesn't matter what you map, and this quantity is nothing but the density of triangles passing through X. So look at the triangle functional to integrate out the two coordinates Y and Z. This is the quantity that drives the regularity. On the other hand, if you have a 2 star, then it matters which vertex you integrate, which you fix. If you fix a vertex which is one of the leaves, then you get this degree squared terms. If you fix the vertex which is the central vertex, you get the degree squared term. And if you fix one of the leaves, you get this term. So in any case, for any graph, you can compute this quantity, and that's my notion of regularity. The other thing that has to change is that the operator W, which was giving me the spectrum, needs to change to something for general H. So this has to be replaced by what we call the regularity operator, which is exactly what Christian said, which W has to be replaced by WXY, which encodes the density of H incident on two vertices X and Y. So again, we have to be careful which A goes to which X and which B goes to which Y. So I fix a vertex A and B of H, and I look at the density of H, where A is mapped to X and B is mapped to Y, and then I average this. So this gives me the 2-point conditional homomorphism density function. And again, if it's a triangle, it doesn't matter which two you fix. But if it's a 2-star, it does matter. So for instance, if you fix X to be the central vertex, Y to be the leaf, or the other way around, you get this quantity here. If both of them are leaves, you get this quantity here.
You don't want to divide there by the.
Yeah. So I am right. So I want to do that, but I'm a bit sloppy with constants depending on H throughout, so that I can fit things in. So this is constant. Ideally, there is a factor of constant here. In the theorem, because I did it like this so that in the theorem it comes a little differently. You know what I mean? So ideally, I want it divided by 1 over VH choose 2 or something like that.
But otherwise, you get 6 times.
Otherwise, I get 6 times that. Yeah. So the constants depending on H are a bit under the carpet just for space issues. Okay, so here's the theorem. It's informal precisely for the reason just mentioned. I am being sloppy with constants, but for any graph H, whenever the true density is positive, if the graph on W is not H regular, then we have a central limit theorem at scale n to the VH minus half, which is what happens when you have 2 copies of H intersect at one point. This variance is 0 if and only if the graph is regular, according to our definition. So if the graph is H regular, which is when this quantity is 0, then again, the limit has 2 parts to it. There is a Gaussian part and there is a non-Gaussian part. The Gaussian part is independent of the non-Gaussian part, and the lambdas here are the eigenvalues of this operator WH, which I just defined in the previous slide, minus its largest eigenvalue. Okay. And I am not writing down the expressions of sigma and tau because those are a bit messy, but we don't need them. They are explicit expressions for them. So these result.
WH is still compact and therefore
it's always exactly. So this is, yeah, it's already.
And you're writing that the multiplicity of the largest eigenvalues increased by 1, but it's a positive operator, right? So isn't that just meaning that you're throwing out the largest eigenvalue?
But there can be 2 eigenvalues which are largest. There can be 2. So 2 disjoint, complete graphs. If you take like both of them, but there are 2 eigenvalues which are the same.
He doesn't assume irreducible.
Okay.
I don't assume. Exactly. Okay. So let me say one line about the proof of how this is done. We can talk about that later. So the proof uses this machinery of generalized U statistic developed by Janssen and Nawicki several years ago. And what this allows you to do is that we can write this subgraph counts as what are called generalized U statistic. And if you do projections onto single variables UI, you get the limit in the regular case. If the limit in the irregular case, if the limit in the irregular case is degenerate, you project on 2 UI UJ, so 2 UA UB, and also on the YABs. And that gives you the limit in the irregular case. That's one line summarizing, the proof, but the machinery is very general. And the machinery is so general that it actually tells us, sort of lets us understand where these Gaussian and these non-Gaussian variables are coming from. And it allows us to prove something much more. So what it allows us is to prove not just single dimensional convergence, but joint convergence for multiple subgraphs. So let's say I have the number of edges and the number of triangles together. What is their joint distribution? We can now do that. So let me set up the notation for it. So we will scale each of them correctly. So we will scale it like this if it is regular, this if it is irregular. Yeah. So the scale is essentially root n or n if you think of it in terms of the densities. Root n for CLT, n for non-CLT. Okay. So I have a graph H, and I define this centered and scale version properly, centered by the mean and divide by the standard deviation VH minus half if it is irregular, and VH minus 1 if it is regular. So this is the correct scaling if I am regular or irregular. And so then the question is, given a collection of graphs H, H1 to HR, suppose I have a graph on W, which is irregular with respect to Q of them, and regular with respect to the remaining one of them. So the most general setup, what is the asymptotic distribution of this R vector? Okay. So let me take a moment to sort of convince you that why this is a somewhat delicate matter than one-dimensional convergence, because suppose I have two graphs H1, H2, if both of them were irregular, then marginally they are Gaussian, so jointly there will be a bivariate Gaussian, so which is fine. You can explain it by the covariance matrix. But let's say both of them are regular, then marginally they are infinite sums of chi-squared. They have non-Gaussian components. So how do you explain their joint distribution? How do you write their joint distribution down, right? So you need some machinery for that, and for this, the language of multiple stochastic integrals come in very handy. So here is the result. So you fix a graphon and a collection of subgraphs H1 to HR, and you denote BT by the standard Brownian motion on 0, 1. And so here is the result. So we have Z, which is the vector of the R subgraphs. It converges to this R vector. Okay, so this terrible notation here, this should be all W's. There's no N on the right side. This is the limit. So this is Z1H of W, and the first R of them, you expect them to be a multivariate Gaussian. So I write this as a linear stochastic integral. So linear stochastic integral is nothing but an infinite linear combination of Gaussians. So this is the Gaussian part. And the other Q minus R parts has two components to it. There is an independent Gaussian component, and there is a quadratic stochastic integral. So this is an infinite quadratic form in Gaussians. So there are various things to note here. So if you note that this function that we are integrating, this is exactly the regularity function. So because we are in the irregular regime, this function is going to be positive on a set of positive measure. So this is a degenerate limit. This function right here is sort of what comes from the 2-point homomorphism densities. And the quadratic components across I are dependent and also dependent with the linear term, and the dependence is captured through this dBT. So these are nothing but writing infinite sums in a compact way, but this is the a notation really for explaining this limit. But the theory of generalized U statistic allows us to write down what the limit is for any finite collection of subgraphs.
Brownian motions.
There's only one Brownian motion. So this is one Brownian motion. One Brownian motion coming from these uniform variables, sort of. So every vertex in the continuum, you evaluate the Brownian motion dx.
I see. Then all your variables are just stochastic
yes,
with respect to this one Brownian.
Exactly. Exactly. So if you think of it like that, then you can see the dependence coming up. Any questions? Yes.
If you're saying that the Brownian motions are coming from the uniforms, what would happen if you would choose your types deterministically?
Oh, that's a brilliant question. So if you choose your type deterministically, I think you only have this part, this G.
So all the other ones are going to
all the other ones are going to go away. You only have a multivariate Gaussian in this part here.
Could you explain to us a little this U statistics where you get the Brownian motion?
Right. So I have a slide in the end, so I can come back to it to explain where it comes. Yes, good. So I remember that. Yeah. Okay. So that's the end of the probabilistic part. So maybe I can now go to the statistical part, which says that what is the implications of this results in inference. So I want to find a confidence interval for these subgraph densities, right? So the way to do it would be to have some idea about what are the quantiles of this distribution. So one thing to note is that the quantiles of these distributions are unknown because they depend on W. But more importantly, I don't even know if I'm in the regular regime or in the irregular regime given a graph. So there are two issues here. estimating these quantiles, but also telling me whether or not I am in the regular regime or in the irregular regime. So to do that, we have a two-step procedure. So first we set up a pseudo hypothesis, which says, let's assume that we want to test the hypothesis that W is H regular versus W is not H regular. Now this can be done because regularity is essentially the variance is 0, and this variance, which I did not write down, but is just a function of subgraph counts conveniently. So I can have an empirical estimate which is consistent, and I know that it scales faster than root n. So this we can show. So we can then do the following. I can say that if root n times this quantity is large, I'm going to reject my pseudo hypothesis. And then I'm going to pretend as if I am irregular, where the limit is normal and the confidence interval is immediate. But what happens if the pseudo hypothesis is accepted? If it's accepted, then I have to estimate the parameters of this non-Gaussian component, which is more non-trivial, which is like not immediate at least. So this is where we develop, in the statistics world, they call it the multiplier bootstrap. So we develop a version of it for Graphons, and which goes as follows. So remember, in the irregular regime, the eigenvalues are given by this 2-point homomorphism function WH. So we can find an empirical analog of this WH, which is essentially an n by n matrix whose S and Tth element is the density of H with one vertex in S and the other vertex in T. So this is the matrix version of W that you estimate from the sample, and then you look at the eigenvalues of that. And the result is that we can show that if H is a graph, you don't really need connected, but let's say it's connected. And I have some IID normal 0, 1 variables, which are independent of G. Then if you look at the sum of the eigenvalues from the second to up to the n of kappa S WS squared minus 1, then conditional on the randomness of G, only on the randomness of this external randomness W, this will converge to the population distribution. So this is a way to estimate the quantiles of this distribution, because this quantity here does not depend on W. It only depends on Gn, which I can see through the eigenvalues and through this external randomness. This is external randomness, right? And it's important to note, just by looking at a quadratic thing, the Gaussian and the non-Gaussian comes out. So that's also part of the proof. So for instance, if H is just the edge, this operator W is just the adjacency matrix divided by n. It's nothing else. So this is just the eigenvalues of the graph. If you look at the eigenvalue scaled by n, and if you look at this quantity for the edge case, this is going to be the estimated distribution. So how do you use it in practice? Well, you use it in practice, you essentially resample this W many, many times to find a histogram of this quantity, and you report the sample quantity.
So, since you're boosting here, why don't you just do plain old boosting? So I just take my graph, I take it as an empirical Graphon, I take many, many samples of it.
But I don't know W, right?
No, you know the empirical W. So why don't you take your empirical W, do many, many samples from that, then you get a new distribution, and now you calculate, say, the triangle counts, you calculate the expectation from this simulated distribution, then you calculate, and then you look what percentage of your distribution lies near to your expectation, and you output that as your estimate. So that would be standard boost.
Yes,
right?
so there are.
Does it not work?
So I don't know. So it's something I think it would be harder to show that it works. This is very easy to show this works. So first of all, I think the proof of this would be easier. And secondly, I would have to think a little bit, how would you resample, right? Because I don't know also the UIs. So one has to think a little bit how to resample the W. There are ways to do it, I think, but it's not immediate, right? It's not like IID, you take a resample, right? So, but this one is a very, very easy way of introducing external randomness, and you can show, just by some whatever moment computation that, this is exactly this distribution, or, we don't, some technique. Yeah.
So your right-hand side has the same limiting distribution as the fluctuations of your
Yes.
H count.
Yes, yes.
Is it independent of it? Is it equal to it if you look at joint convergence?
Right. So the joint convergence will require us to use sort of the same Gaussian for the edge and the triangles. I'll come to that. So this is only for one dimensional. I'm only doing the one dimensional estimation problem first. So I will do the joint convergence in just a second.
No, but I mean, you're adding extra randomness here.
Right.
So how is that extra randomness related to the randomness that you see in your H counts?
This is W1, W1 are independent of the randomness of G.
I understand, but is your limit then also independent of the limit you would get for your H count?
You mean the limit doesn't depend on whether you take Gaussians here or any other centered variables? Is that what you're saying?
No, I mean that the right-hand side has the same marginal distribution as the fluctuations of the number of H bars. It's the same marginal. It's the joint distribution.
So we don't know that, but that's a good question. Yes, we haven't looked into that. I see what you mean. So you're meaning if I look at this one and the actual count.
Basically
Yes.
asking whether
Yes,
W
yes.
squareds are adding extra randomness to the right-hand
Yes,
side
so-
or they don't. That's not
So we
entirely
did not
obvious,
look
right?
at the joint distribution of this one and the population version, but that's a good question. Yes, yes. Okay, so let me summarize what is the final algorithm for one-dimensional confidence sets. So if you have the pseudo hypothesis, if the pseudo hypothesis is rejected, I go for the classical interval. If the pseudo hypothesis is accepted, I go for the interval that comes from the multiplier bootstrap. And the theorem says that for any graph H and Graphon W, the interval that comes out of this process will have coverage 1 minus alpha for any density, for the density TH of W. Alpha is a pre-specified parameter, which is your coverage of the interval. So alpha is 5%. Alpha is 5%.
Theorem is for alpha, for all alpha.
For all alpha, dot, dot, dot. Yes. Right. So all of this extends to joint confidence sets. So now suppose I have R subgraphs and I want to find a confidence sets for the R densities together. So I will be a little bit like high level here, but what's essentially what you do is you look at the empirical versions of these 2-point homomorphism densities and the empirical versions of the 1-point homomorphism densities. And you have this pseudo hypothesis set up for each I. And if depending on which of them are accepted or rejected, you set up your Z hat. Okay. And you add this external randomness ZS and ZS ZT. So this is where the name multiplier bootstrap comes in. You can add in this external randomness. And now you have this vector. You have this vector. So these are, what I just mentioned. So this vector Z hat is Z hat H1, Z hat H2, Z hat HR. This you get. All of that doesn't depend on W. It only depends on the graph G and the external randomness. And it has the same asymptotic distribution of these GNs are all going to be W, but the actual distribution of the thing that we want.
So how does your hypothesis rejection or exceptions will also depend on alpha, right? Because
No. So that hypothesis, I have no alpha in it. That hypothesis I am doing, that's a good point. That hypothesis, I'm just rejecting it at 1. Because this thing goes to 0 at rate root n. So it doesn't matter asymptotically what constant I take here.
I see.
Yeah.
Also, like it's not tilde like the hypothesis not regular.
No, so because you see, this is large, that means it is, I am in the
Rejecting H naught, right? So I think
right. So
somehow I think
if it is regular, it will be 0. If it is regular, it will be 0. And if it is irregular, I will reject this is large, so I will reject if it is irregular. So it is 0 if it is regular.
Oh, I see. Right. So
It's a right. Okay, so so that's the high level summary of what the confidence set is doing. Yes.
Another question about precisely that point. So you've gone all the way back. I'm sorry about that.
Yeah.
So you're rejecting when your threshold variance is larger than 1. But then wouldn't you also need to know that that product actually tends to infinity if you're
Yes.
irregular?
Because I know that if it's regular, then this is 0. This is a consistent estimate. This converges to something positive under H1.
Yeah, something positive.
Yes.
But is that something positive larger than 1?
No, but it's something positive without scaling.
Ah, without scaling.
Without
Okay, I see. Yeah, that answers my question. Thank you.
But sorry, just operationally, you could replace 1 by any point.
Yes, operationally, this matters. Yes.
And you could actually even replace it by some n to the right power.
I could have this scales like n. So I know the distribution at scaling.
Right.
So we could replace it by that, but it's slightly more hard work, so I'm cheating a little bit.
Yeah, but you could instead of 1 do something which grows slowly
Yes,
and
yes,
or
yes,
falls
yes,
slowly with
Yes, yes, absolutely, absolutely. Okay, so so that's sort of the theory from a high level on what the confidence interval is doing. Let me show you some pictures to see this is actually working. Okay, so quickly some pictures. Okay, so this is the edge density of, this is estimating the edge density. So let's have a graphon which is x times y. So this graphon is edge irregular, of course. If you compute the degree function, it's not a constant. So I can run the algorithm and I can compute the confidence interval for the edge density 100 times for a graph of size 300 generated from this graphon. And I see that only 6 out of 100 times it doesn't contain the true value. So I have excellent coverage. Remember, the algorithm doesn't know if I'm regular or not. It's running, it's doing this testimation thing, test and then estimate. So let's now take another example where I am in the regular case. So this is the graphon corresponding to the bipartite graph with 2 sides of size n.
So go back to your thing. You don't want to just cover, but you claim that you say your probability of lying in that is 0.94, right?
Is asymptotically 0.95. Yes. So you would expect this thing to be not too large, not too small. Neither is good.
Right.
So we are getting pretty close here. Okay, so now let's consider a graphon which is degree regular, where you have 2 blocks and the edges between them come with probability half. So this is the random bipartite graph model. And this graphon is edge regular, every edge density is quarter. And again, you can repeat this on a graph of size 100, and you see that, coverage is pretty good. So that's for 1-dimensional confidence sets. Let's try to do some confidence sets for 2 parameters. So edges and triangles together. So this graphon is x plus y over 2. Again, is neither edge regular, not triangle regular. So you can easily check that. And so we can run this 2-dimensional algorithm, this 2-dimensional multiplier Bootstrap, and see what comes out of it. So this is a heat map of 100 ellipsoids, 100 confidence ellipsoids over graphs of size 300. So what it means is the intensity of a point is proportional to the number of ellipses it contains. And again, you see that this is the true value, and the true value is contained in 94% of the ellipses. You can see that there are some bad ellipses, of course, but we have still good coverage. So there are 4 possibilities here: triangle regular, triangle irregular, triangle regular, edge regular. So 4 possibilities. So we will do all the 4. So this is a case where the graphon is, can't see the gray here. So you can see the gray here? Okay, good. So, okay, thank you. So this is the graphon, which you can see there. This corresponds to taking a complete graph of size n over 3 and a complete bipartite graph of size n over 3, n over 3. This graph is edge regular. Every vertex is degree 1/3, not triangle regular because there are no triangles here, lots of triangles here. And again, if you repeat this quantity and if you run the algorithm, great coverage. Let's take a graphon which is edge irregular, but triangle regular. So here is one. So this is slightly harder to construct. This is a graph which is edge irregular, but triangle regular. So I have 2 complete tripartite graphs, and I join them by probability half. Every vertex here has the same triangle density, but here the edge density is different. Okay. So this graph is edge irregular, but triangle regular, and again, good coverage. And finally, the last one, we took an easy example of a graph which is both edge and triangle regular, which is if you take the Edoshreni graph, which is of course regular for all values of edge, and again, the coverage is good. So let me, I don't know, I'm almost out of time, but spend a little moment to talk about the last part, which is sort of the combinatorial part, where we will discuss some degeneracy issues of the limit. And this is only going to take 2 minutes. So I know that the distribution of the number of copies can be Gaussian, but the Gaussian limit can be degenerate. Then you have this non-Gaussian plus non-Gaussian part. So if the graphon is regular, you have this scaling, and under this scaling, this is the limit. So a very natural question is this limit always non-degenerate? Right? So is it true that this limit also can sometimes be degenerate? So that would mean there's more to come. So the question is the limiting distribution of ZHW always non-degenerate? So Hartley, Pelekis, and Silekis showed that if H is a clique, this distribution is always non-degenerate. There is nothing more to come. That's it. So when we were starting out on this problem, we thought, well, for general subgraphs, this is also should be true, that this is it. So we tried to give a general argument, but we were struggling. So we started with some very specific small subgraphs. So what is the smallest subgraph after cliques, which is kind of regular? That's the 4 cycle. So we showed by an argument that is very, very specific to the 4 cycle, that if you take H to be the 4 cycle, then the limit is always non-degenerate. Okay. And the argument also worked for the 2 star, so K1, 2. So we know 4 cycles, we know 2 stars, and we know cliques. So now the next step would be, so how much can we push this, and what can we say about larger graphs? And so we were trying a bunch of things, and in particular, we wanted to see what happens if you take the R star, K13, K14, and so on. And it turns out that if you have K13, there is a surprisingly simple example which tells you that even the second order limit can be degenerate. And this example is very easy. You take H to be the K13, and you take WXY to be the bipartite graphon. So 0, 0 on the diagonal, 1, 1 on the off diagonals. And we know this graphon is regular. You can check that, which means that the normal limit is 0. We can check that this graphon is also like second order degenerate. So the normal plus non-normal limit that you get from the second order is also 0. So both the limits I showed in the theorem are both 0 here. Right? And so the question is, what is the limit? So in this particular case, you can find the limit by an explicit computation, because this is a specific example. And it turns out the limit here is a 4th degree polynomial in Gaussians. In particular, you get the 4th Hermite polynomial.
But sorry, you then also have to scale again differently?
I did much differently. So this is supposed to scale like, you know, VH minus 1, which is supposed to be 3 or something, or I suppose much smaller scale. Yes.
Can you show me the original limit theorem?
Yes.
So I don't quite.
Oh, well, that is fine.
There it was.
Oh, oh, you mean just that limit? Oh, that one, yes.
The first term is Gaussian, independent of the second term, right?
Yes.
So
but
how can this be?
But this variance is 0, and this variance is 0.
Okay, that variance. That is.
So I will come to a question of individual degeneracies in just a moment. So you can ask, when is this degenerate but not this one, and when is this degenerate but not that one? Okay. So that's the last point, and I will stop. So I'll end with some questions, of course, because this degeneracies raise some questions. And where is that? Okay, so questions. So for which graphs H and which graph on W is the second order limit degenerate? We don't know. Okay, we have no idea. Can there be arbitrarily high order of degeneracy? So can you construct a graph H and a graph on W for which the limit is arbitrarily ordered degenerate, like up to order R or something? I don't know. You can ask a question which Remco just pointed out, that what if you know that the limit is non-degenerate? What is the structure of W if one of the components vanish? If the limit in the normal component vanishes or the non-normal component vanishes. So when is the limit normal free? Which means when is the chi-square limit degenerate? So for this, we have a relatively good answer, but let's not go into that. let me sort of mention the question. So when is the limit normal? So the limit is normal if this chi-square component is degenerate. So an easy sufficient condition for it is that the spectrum of this operator is empty. So that means this operator is a constant function. This 2-point homomorphism density operator is a constant function. So of course, if you take W to be the Edoshreni graphon, this happens. But are there other graphons for which this happens? So the question is, are there H regular graphons for which the limit is normal? Then that would imply that the function is a constant, the WH is a constant, W is a constant function. In other words, are there graphs which are not Edoshreni for which this limit is normal? And the conjecture is that probably not. So of course, for edges, it's not. For triangles, this is connected to some result of forcing quasi-randomness using triangles by Reihar and Scott. And they showed, and a consequence of the result says that for triangles, the only graph which is regular and has a normal limit is the Edoshreni graph. And so what happens for general subgraphs? So that's there. And so I'm going to stop there with the question in the end, but thank you. Sorry for going over time. Thank you.
Okay, thanks so much for the engaging talk. Are there questions?
Yes, Christian.
I wanted to still show me the
Oh, yeah. Okay, so here it is. So where is the thing coming from? So this is for the edges, just to be easy and specific. So I look at the edge density minus edge count minus its expected value. I write it in two ways. I first add the conditional expectation given U. And then I write the other term, which is the conditional expectation minus the actual expectation. So this quantity is a conditionally centered stuff. This is essentially if you condition on U an IID sum. So this is what always gives you a central limit theorem, a classical central limit theorem. If you look at the other term, which is the conditional mean, that quantity is WUIUJ minus its expected value. So this is exactly what they call a U statistic. This is an order 2U statistic, right? And if the graphon is not regular, then this will have variance n cubed. But if it is regular, then its variance becomes n squared, and this becomes a degenerate U statistic. So then you have to sort of go to the spectral properties of U to, find the limit.
In that case, the U statistics will involve this Brownian motion.
The Brownian motion is always there. So so essentially you can write this quantity sort of, as think of these linear combinations. If you have a normal distribution, right, you can think of it as, normal 0 sigma squared. You do the projection onto the vertex UA. So you look at the conditional expectation given UA. That is the function value at the 8th vertex. So the normal will be integral of FA dBA. So, that's the Brownian motion.
The other one?
The other one is, again, when you do the projection on UA and UB, two of them. But it's the same Brownian motion because they are coming from the vertices. Yeah.
Can I see your open problem slide?
Oh, yeah, thank you.
Yeah. For this question that relates to the forcing pair.
Right.
Yeah, is there a general correspondence between the forcing pairs and these normal Z?
Yeah, so this is something I don't really know. So the question is that if the 2-point conditional homomorphism functions are constant, what does it mean about the actual function W? Does it mean the actual function has to be constant? So for triangles, this happens to be shown in independent, different work related to forcing in this paper. And it's conjectured for any clique. Now, I'm not sure, whether, certain graphs you need to fix 3 vertices. So I don't know. There are lots of results in quasi-randomness, and I don't know exactly how it fits into. But the question is, can you find graphons for which the limit is normal, even though it's not Edoshreni? or whatever, the graphon for which WH is a constant graphon, but W is not a constant graphon.
Okay, so what you want is for fixed pair of vertices, you want to have the same counts for
Yes,
your H.
but the original W is not. And also I want to have the degree to be constant. So there are two conditions. The graphon has to be regular and pairwise regular. Let's put it this way. Does it imply that it is actually fully constant? I don't know. Yeah, probably for general H, it might not be, but it's conjectured for cliques in the paper by Heidke and proved for triangles in a different paper.
Yeah.
Oh, well, I loved all your results. So I think your theorem seems to imply finite dimensional convergence of Brownian motion, right?
Yes.
So how difficult would it be if you go one step further to show the process convergence, say in the spiral copy?
Yeah, so I'm a little, so that's in the case where everything is the normal, in the case where everything is the regular regime, probably doable. But if you go to the irregular regime, I don't know. And this is something, I don't exactly know the technicalities to fill the gap, but I think the idea, what I said, higher order graphon theory in the title, was to say, can we find a whole process convergence, some sort of, whatever that means, of the graphon? And we have the finite dimensionals, so there's a bit more to do, but yeah. So that's a great question, yeah.
There's a question here. Oh. Thank you.
Two quick questions. One, statistician, still bothers me that your test is not really necessarily practicable.
Yes.
Is there a way for you to turn that into a asymptotic procedure that will be able to do testing and estimation at the same time with given coverage?
So the part that bothers you is because of the one?
Yeah.
Okay, so that part is because I am lazy. So that part,
so you can,
yeah, I can do that because I can find the distribution of that quantity and I can make it better.
Perfect.
But we are a bit lazy.
Yeah.
So we did that like that. Yeah.
The second question is that, do you have a sense of a speed of convergence to the limiting distribution?
Okay, so for the Gaussian case, yes, Adrian and others have certain results using Stein's method where you can find the rate of convergence in the Gaussian case. In the non-Gaussian case, I don't know. It's harder, I think. Yes.
Thank you.
Yes.
Other questions? If not, let's thank all the speakers. Thanks for participating in the first day, and there is a reception outside.